Howdy folks, Mr. Holderman here. We're going to pick up where we left off in class, starting with Ohm's Law. So Ohm's Law, you can read the definition at the top, but remember that we're going to focus on this definition right down here at the bottom, that equation. So V equals IR is often just synonymous with Ohm's Law. So that's probably the most common form that you'll see it in. Obviously, we can rearrange it to look at the other two versions, but we're going to stick with V equals IR as the one to remember. So let's do an easy example to start off. This is just one where basically plug and chug, but it'll give us the basics of a circuit. So let's start by reading the question and drawing a picture. So the flashlight shown uses a 6-volt battery and has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn by the battery? So when we draw a schematic, which is the circuit diagram, we want to include the battery. That's our symbol for the battery. So the big end is the positive side. The little end kind of looks like a negative sign. That's going to be the negative end. And when you draw a circuit diagram, you always want to use right angles to keep it pretty clean for your conductors. So the battery connects to, we've got here, this is a generic symbol for a resistor, which you'll see more of these symbols in the activity for this week. But we can assume that's the battery, or I'm sorry, that's the flashlight, and then it comes on back to the negative side. So always flowing out of positive back toward negative. Then we want to label everything. So we know that the battery has a difference, a potential difference of 6 volts, or voltage of 6 volts. And then we know the resistance of the bulb is 150 ohms. So with that, we want to find how much current is drawn out of the battery. And so it's pretty common, you'll see that we have the total current. So current is I. Total current comes out of the battery, goes through this all the way back around. So pretty simple example. We look at our equation, V equals IR. Since we're solving for I, we can go ahead and rearrange that. I is V divided by R. Then just plug in our numbers, so the voltage that is dropped. And when we're solving for this, we're solving for the whole current, but also this is the current that's going through that component. So when we plug in numbers to the equations, it has to be for a specific component. So the voltage that is dropped over this component is 6 volts, because there's only one component in it. So 6 volts, and then the resistance across that is 150 ohms. So when you plug those in, you get 0.04 amps. So pretty small current going through there, which is a good thing for a light bulb, so the wires don't heat up. But just as a reference, that's a good number for a current in a small device like this. So let's next look at general series and parallel circuits, which I know we did in class, because we're going to put components in a couple of these and then draw some circuit diagrams. So it's important to know that in a series circuit, all of the components are connected end to end. There's only one path for the electrons to flow. And then in a parallel circuit, there are different paths. So remember, each blue branch point here, the electrons can flow one way or they can go the other. So that's key for drawing these out and figuring out what type of circuit you're working with, because the rules are different for each. And we want to look at some of those rules, and so we get Kirchhoff's laws actually, and we have two of them, one for series and one for parallel. So Kirchhoff's voltage law says that the sum of all voltage drops in a series circuit equals the total applied voltage. So let's go back to our series circuit and see if our first component is a battery, and we have 3 resistors in there. The voltage drop, as we said in class, has to be dropped across each of those components, and it has to total to whatever that battery has. So if you're an electron, if we said if you're an electron, you have 6 volts to give, and you have to cross 3 tolls, 3 resistors, you have to give up a certain amount at each toll, and you have to have some left over. So Kirchhoff's current law for a parallel circuit says that the total current in a parallel circuit equals the sum of the individual branch currents. So again, let's go back to that picture. Assuming our first one is a battery, the other 3 are resistors. If we are electrons leaving this, we all have to come out of this battery. But then at this first branch point, some of those electrons go down this path and some go this way. Now the ones that go this way, we've got another branch point here, so some of them split off there, and some of them go to that third component. So we get some going to each branch, and then they all meet up back at this point so they can all flow into the battery. So the current in all three of those branches added together is the total current leaving and coming back to the battery. So that'll be important when we try to figure out the individual components of each circuit. So a little bit about series circuit. First of all, that we know there's only one path to current for current to flow, and if we have a complete circuit, in this case both of the light bulbs will light up. But wonderful animations here. If one of those bulbs leaves, or if you turn the switch off, if there's no path for the current to flow, it won't jump over that gap. There just simply won't be any flow. So let's take a look at a specific example. And this might be where you want to pause and write this stuff down in your engineering notebook, because we're going to use these principles to calculate this problem. So we know that the current flowing through every component is the same, that's key principle, and the total resistance in the circuit is equal to the sum of all the resistances. So let's look at that in this specific example. So when we draw out a circuit diagram, again, we want to draw nice right angles, and we want to include every part. So we've got the resistors, R1, R2, and R3, and it's good to write the resistances with those, so R2 and R3, and then it might also be helpful to label. We have the current going through the entire thing, and what our goal is for this is to find out V, I, and R for every single part of the circuit. Now, when I say parts, I'm talking about over these components. We already know a little bit about the battery. We want to find for each individual component and the total circuit. So we're looking at the total current there. And the way we can do this is by looking at, Mr. Schmidley calls this a circuit puzzle. So in a circuit puzzle, we have the voltage, current, and resistance for all of the pieces of the puzzle. There are three resistors, and then we want to find the totals. So we want to fill out just like a Sudoku puzzle. We can use Kirchhoff's laws and a little bit of circuitry and mathematical wizardry to figure out all of these pieces. So when you start with one of these, you write out everything you know, and then what we're going to do is called collapsing the circuit. And when we collapse the circuit, let's pretend this is a traffic jam. We're going from work and we want to get home. If this is our path to take, each one of these resistances is like a little traffic jam or stoplight. So if we are these little cars leaving, we have to go through this one and this one and this one in order to get home. So instead of saying that, maybe each one of these is 10 minutes, we could just draw one circuit and assume that all of these are added up to give us that total resistance. So if I were to ask how much total time did it take you to get home, you would say 30 minutes because you stopped at 3 stoplights or 3 traffic jams. That we want to represent by one resistor that is equivalent to, our example, 30 minutes. But in this case, we want to do it with resistors. So we're going to copy the information that we know. We know this battery is still 12 volts, and then we want to figure out how we get that one resistor. Now, it said on the previous screen that in a series circuit, the total resistance is given by this equation. And this is a pretty simple one. R1 plus R2, R2 plus R3. So it makes sense. If we're leaving the battery, we have to go through all of these, so we might as well call it total resistance. It's all the same thing. So when we add R1 plus R2 plus R3, add those numbers up, you get a total resistance of 1,890 ohms. And so let's take a look at our logic puzzle to see where that gets us, because we already know a little bit about it. So let's go through. So do we know resistor 1? Do we know its resistance? Yes. So we just kind of use that, 220 ohms. Do we know R2? Yeah, it's given, so 470 ohms. And R3 is given 1,200 ohms. We're just kind of filling in what we know. And then we just calculated that total resistance. So we can write that over here. We can write it right there. We don't want to get too sloppy, but let's write it right here. We know the total resistance in the entire circuit is 1,890 ohms. Okay, now do we know anything else? We do, but we're going to hold off on that for just a second. So when the purpose of collapsing the circuit is because now this looks like the example we just went through where we have one voltage, one resistance. It's very easy to calculate the current. So all of the current leaves here, goes that way. And if we look at our first picture, that's the total current that we're solving for. So by collapsing the circuit, we learn one more piece of information. And we can do this with V equals I R. But now the I is for the total current and the R is for the total resistance. And we already know that the total voltage is 12 volts because that's for the whole circuit. So when we solve for our total current, I is equal to 12 volts over our total resistance, 1890 ohms. And so we get a current of 0.0063, what is it, 634. Give it a few decimals. If you can use the unrounded value from your calculator, do that, because that would be ideal because you're going to use that number a few more times. But now we know the total current going through the entire circuit, so we can write that down here, 0.00634 amps. Okay, well, since we collapsed it, that's obviously not the whole circuit. We got to go backwards. So once we figure out the total current in this case, we know every bit about it. We know the voltage, current, and resistance. We have to go backwards using that information and figure out what else we can figure out. So we go backwards up there, looking at our first circuit, we know the total current, and in the series circuit, we also know the principle that all of this current has to go through each component. So we can go ahead and fill that out in our circuit puzzle, and that'll help us get to that very last piece. So the current is the exact same all the way through. 0.00634 amps. And we could rewrite it, but for the sake of time, there we go. The current is the exact same because that's the principle of a series circuit. Okay, next up we have the voltages. Now we want to figure all of these out. We want to figure out the voltage for each component. We also want to know the total voltage. We already know the total is 12 volts, but that is not entirely useful anymore because we know that those 12 volts have to be dropped over each of those three components. So the 12 volts is no longer useful. When we look at the voltage drop over one individual component, we have to look at the other two variables because that 12 volts is going to be split amongst all of them. So if we take our first resistor, we know we have a resistance of 220 ohms, and we know we have a current of 0.00634 amps. So for V equals I R, we have to look at each individual component. So let's look at the current through resistor 1, which we know is over there, but it's equal to the total current, and the resistor number 1. So this will give us the voltage drop across resistor 1. So plugging that in, 0.00634 amps times 220 ohms. And for V1, we get 1.39 volts. Give it a couple decimals there. So that's for resistor 1. We can go ahead and put that in our circuit puzzle. 1.39 volts. We can do the same thing for V2 and V3. But keep in mind that we have to do these for each individual component, and we have to use the numbers that go with each individual component. So we're looking at R1, we're looking at only those numbers in that row. R2, only those numbers, and same with R3. So the same equation, so and our current is the same, so we can go ahead and plug in 0.00634 amps, because all of that current has to come through resistor 2. And then we have a resistance at that point of 470 ohms. So if you multiply those two together, beep, 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 you get 2.98-ish amps. Now I'm rounding these numbers. So let's go ahead and put that in 2.98. Oops, upside down. Volts. Voltage is measured in volts. Then we've got a couple things we can do with that R3. I'm going to go ahead and calculate it because I know the numbers. So V3 is our total current times our resistance. And we should get 7.61, and not make that same mistake, volts. So we could plug that in here. The other thing that we can do with that is to look at it, and this is where Kirchhoff's law comes into play. So for a series circuit, we know that all of the voltages must add up to the total voltage. So we had 12 volts to give at the beginning. Across resistor number 1, we gave up 1.39, so you subtract that number. Across resistor number 2, we gave up 2.98 volts. And then the amount that we have left is what we drop over resistor number 3. So either way we do this, by subtracting those two numbers from our total or by calculating it, we should get 7.61 volts. And if you round it, it might be 7.63 or 60 or something like that. But those three numbers should add up to your total. We've dropped all of our voltage across each of those components.